Okay. Good afternoon to all of you. Uh, Thanks for coming and thanks for inviting me to give a tutorial. Uh, so I think the title in the which I gave you was a very bland looking title, Introduction to QML. The reason was I was myself confused what to speak for 90 minutes, the tutorial. Uh, See, I have experience in machine learning over the last 25 years. That subject I think I understand well. And seamless admission, quantum I know nothing about. So it's more about I'm also as much as a learner as many of you. And a good thing about giving a talk like this is maybe most of you have no more than quantum than I do. So what I thought what I will do is, so in this talk, I mean, what excites me is looking at foundational methods, algorithms, and things like that. So I will not talk about how in the space of AI and quantum algorithms have been invented and that has been applied to many things like finance and biology and things like that. This talk is not for that. So in my understanding, in my reading, there are certain very key ideas which I think are very useful, and I'll take the opportunity to present that to you. That's why I called it, introductory survey of ideas. And given this time, there's also this challenge, right? I mean, depth versus breadth. So I'll try to cover more breadth, give you references as we go along. And in-depth discussion, I know something I'll happy to share outside the scope of the talk. Right? So that would be broadly the agenda. Yeah, so any questions you may direct emails to me and we'll see. Now, so of course, the slide has to be there, the TQC happening, International Year of Quantum and things like that, right? So look, the quantum science has been there for a long time. But quantum computing, what does it mean? So that's something where all of us are perplexed. Many of us are amazed at the potential it has. But to realize the potential, what do we do? And that is the reason I think UN has declared this a year of quantum. Now, from my earlier days, when I was a student 25 years ago, in this campus itself, there were talks on quantum and things, and quantum algorithms, things like that. But if you look at those talks, there's a distinct flavor. Somewhere, someday, somebody will build a quantum computer. And what kind of algorithms will that computer run? Those were the times. And then a lot of research is still going on like that. Oh, look at these things, right? This has arrived. So how can we make use of that? So that's the kind of things which is amazes me, interests me, and also some of my research has been like that. So to that end, I have picked certain ideas, and we can talk about that. These are general things, right? So now here's a pitch for what I do. I have also not gotten obsolete yet. I think the generative AI is the big thing, right? And now you don't require me to tell you this. That, for example, I think it was quite fun. July of last week of July, I was visiting Google India here for just a talk, and then everybody was so preoccupied. Not that I'm giving a talk, people will come. Maybe they don't want to come to my talk, but I said, "What's happening?" Oh, no, we are very busy. Of course, you are busy. What are you doing? No. Math Olympiad is on. So as Math Olympiad is going on, they were training their models, and there was a competition between OpenAI and Google and all that. So now nobody could imagine the right mind that, some machine's going to solve complicated problems like Math Olympiad problems. This era we are living in, right? I mean, this is, of course, one can ask what use that is. That's a different story. But needless to say, it is changing the way we do things, disciplines, right? No discipline will be untouched by AI, and especially generative AI. So what is the word generative AI? Maybe hopefully we'll go along discussing it. So the difference that I'll be able to synthesize new things. So that is the power it brings to the table. Now, And now here is where I see a potential, very interesting connect to quantum computing, of course, among many other things. So generative AI can be thought about as generating instances of, let's say, a new face, like solving a solution to a problem which you have not seen, right? Those instances. Uh, I think many of us use ChatGPT. Time you ask ChatGPT a query, it gives you something, and that is not written anywhere. Generate some text with answers, right? The generative AI. Now, where's the foundations like? So now, so there is this thing in machine learning called latent variable models. Latent variable models. We'll explain them as we go on, right? So most of it can be viewed from that perspective. Underlying this latent variable model and is doing all this magic it is doing. But of course, so this has been around for 30 years, so why nothing happened? Of course, compute didn't was there. Deep networks magic didn't happen. All of this has powered today's models like ChatGPT, Stable Diffusion, and so on and so forth. So now, here is, actually I've been asked to give talks, even in this campus also, at, just to celebrate this Nobel Prize. That, but see, if you see Professor Hinton's research, most of the papers have not appeared in physics journals. But why does it deserve the Nobel Prize? So this is the actual citation at the Nobel Prize website, right? So now, so that is where he wrote a paper in 1985. It's called Boltzmann machine that has been cited here. Now this is a first instance of a generative model. In many ways, he has laid the foundation of today's magic. And Boltzmann machine is essentially a very nice, let's say, abstraction of the famous Ising model in statistical physics to real-world problems, or images and things like that. There's a right marriage of things. You take a concept in some other field, abstract it out, and apply it. And you can see, I know, hopefully you'll explain some of the things, right? Okay. Some pictures will hopefully come. So today, as of now, just to connect to real world, that was 1985, right? The idea was languishing. It was grown and all that. Didn't have the compute power. In 2009, this paper changed everything. So in just like any field, you will have some sort of a like a problem to demonstrate your ideas. So this is a very famous data set called Emnist data set. This is basically digits, right? Handwritten digits. Now the idea is that can you recognize them accurately? You have a fancy algorithm, okay? Can you recognize this? The implication is if you can do this well, you can do other things well. So this is like any field will have some of this, some basic things, right? So this is Emnist data set. Now they beat all other algorithms off the park using deep belief networks, right? And the seed was in that Boltzmann, right? Now, today, this is, as you can understand that this is where I come from. So I'm curious, for example, quantum, exciting things, right? But are there models in quantum, computation and things like that, which can, for example, beat RBMs on the data set? Okay. Now the thing is, for example, ChatGPT, for example, you can ask them to generate images, right? So other models which can generate like something like faces to it. Can you do that? So that was the thing which started all this discussion. So this is the bias I bring to the table when I select my problems and areas, right? So by no means what I'm going to say is exhaustive in the papers you're going to show and things like that. But it would be, let's keep this in mind. This is where the perspective I come from, and that's why my selection of ideas is limited, but that is no ways reflective of the whole field. So basically, if you want to think about structuring the thing, right? So what are the promising directions, which intersection of AI and quantum computing? When I'm promising, I mean, of course, application has to be the thing, you must apply things, but most importantly, are there new science to be done? Do you need to develop new algorithms, new things? So those I call as directions, right? So you can identify them, and that is a thing. Also, can you characterize, maybe that's too much of a heavy word, but can you now recognize that these problems may be the right fit for a problem, or like this. And then, as I said, 20, 30 years ago, there were these nice talks, this campus and everywhere else also, that there's quantum algorithms, and in the near future, somebody will build a quantum algorithm and do things, right? But the question is, are they realizable now? Because we saw those things. 1,000 qubits are there. So press is saying, I do not know how true or false they are, but they're there. So those are the things we want to think about, right? Now, to that end, here is our agenda. So supposedly, this agenda can think about this, right? Like quantum computing has some primitives. What's the primitive? I'm thinking like, let's say Grover's algorithm is a primitive, right? Same machine learning also has a primitive. So what I'll do is in the first, and my assumption is that this group has a good expertise in quantum computing, may not have an expertise in machine learning. I make this assumption. And to that end, what I thought is we'll do is we'll quickly go over some ML primitives. And now this is not a, please don't take this as a class for ML primitives. That is a mistake, because then he will say in 30 minutes this guy has finished all ML. I don't like to know that. I want to say no, you should go and just do a course or a PhD and things like that. So this would be more like, what are the quantum analogs, please? Are there any? To that end, maybe that's the second part, would be a more like survey of quantum analogs for such models, right? And thirdly, time, the research effort in our direction, in our group, we will share some of them if we get time. So this would be mostly the agenda of time, and then, and I'd also like to keep it like that. I don't have to finish all the slides. You're most welcome to ask me questions, stop me. I'd like it more to your discussion. Okay, and repeating again. So when I prepared this talk, it is mainly aimed at non-expert ML, who may have exposure to quantum computing, and but by and large want to explore quantum computing with ML focus in mind. Okay, yeah. Okay, so now with this, so agenda follows. So machine learning, I think many of you are probably aware, has many paradigms, but in my understanding, if you want to say quantum ML, it is pre-1985. So what Hinton is concerned, it is as pristine as that. Quantum ML. I'm not saying quantum, not say AI. I'm saying quantum ML is good. We don't have models like that yet, right? So at that point, if you have machine learning, there are basically two strands of research, or three strands. Basically, supervised, unsupervised learning, reinforcement learning. Today, there are many more threads, right? So I'm thinking like that. Can we take those basic threads and discuss? So what I do is we'll talk certain primitives in supervised learning. So namely, perceptron. So this was an algorithm in 1950s. In those days, with limited media coverage, it was as big a deal as today's GPT. That amount of noise in 1950s. So that's the algorithm. Today probably you'll say, oh, it's a classroom, 10 minutes will do, and nobody uses this. There are more sophisticated things, right? So we'll start with that. Support vector machine is another idea which has ruled the 1990s, but by and large now obsolete, but still may have a new play in quantum. We'll talk about some interesting mathematical analogs called kernel functions, which helps in some of these algorithms. We'll touch upon, so these are, we at the perspective of, remember the images I showed you, 0, 1, 2? Now, things like this, you're asked to build a machine where I show you some zeros and ones. And then you're tasked with this. Next times, you'll be able to identify whether the image is 0 or 1. So with that perspective, you can think of the first three things, right? Now, next, you can say, okay, I measured the sensor readings and how cold this room is going to be, and pressure, temperature, all kinds of things, right? So you can put a real number. And for that, regression is the way to go. And rigid regression idea in 1950s again, but was very useful in many practical problems. So we talk about rigid regression, right? And then we talk about how kernel functions can apply to this. So next we'll touch upon the so-called unsupervised learning. So the difference is in the first problem, as I said, I've shown you these images of, and I told you this is 0, this is 1, right? You know that. And I asked, now build a machine on that. Now think like this now. I give you the same set of images, don't tell you what is 0 and 1, and ask, go figure out what's happening. Right? That's unsupervised learning. The supervised signal is the 0, the fact that I told you 0 or 1 in the beginning, right? So that is the broad scope, right? And now to that end, we will talk about the famous Boltzmann machine, of course. There's this notion of, so sometimes in that case, right, there's zeros and ones, and I told you there are 0 and images, and I asked you to find out something. So there are many ways to formulate it. One way of formulating it, see, data lies in a low dimensional manifold. How to identify the low dimensional manifold? So principal component analysis, PCA, is one of those primitives. Okay, so we'll talk about that. And lastly, we'll talk about EM algorithm. Now, this algorithm was invented in 1970s. Now, today's many of this AI magic you see, back up the pie, this is the algorithm which is running. Okay, so we'll not be able to cover that whole ground, but hopefully get these things. And now the question is that this is not a class about all of this. Now, as we are going through the slides, I'll go through these notes. I want you to think, what is the quantum analog of this? And that will lead to the survey of ideas, right? Okay. Yeah, sure. So maybe if I can sit there, that's a better way. Otherwise, manipulating this is a... Okay, I'll not write anything, but what happened? Yeah. Okay, so now let's begin with this story about those zeros and ones, right? So let's arbitrarily name them. -1 is, let's say, a cat, and 1 is a dog. And what is X now? X could be, you have got an image has pixels, let's say 100 pixels. Now you can take the pixel value. It could be black and white, 0 or 1, it could be 255, some numbers. So that is, you dump on me a vector of 100 dimension vector. So cat means 100 dimension vector. Signal is 1. Dog is 100 dimension vector. Signal is -1. You shown me 1 million images of this. Question asked, okay, that's funny enough. Build a machine which will take this new image and tell me it's a cat or a dog. That's standard setup, right? So now, of course, so suppose they have a data set. This is called the training data set, right? And so one way to learn this is first thing, without bothering about any complicated science, is that, okay, on my training set D, I should be able to classify everything correctly. The first approach. Okay. So you see, I have to come up with a classifier. What is the classifier now? Classifier is, it takes in an image that is X and gives me an output 1 or -1. A function like that, right? So that function, so first criteria is come up with a function like that, any format you like, and they should match these values on the training set. The first attempt, right? Okay, so this will be my classifier, right? Now we can let's think about the linear classifier. Oh wait, what's the linear classifier? Now I say that the function, is I have to match 1 -1, no? So let's compute a linear function on X and take the sign of it. Okay. So how far can we go? Right. So that's sometimes called a linear classifier because the linear function on X is the key computation, and sign, okay, fine. Sign is not a big deal. Right. So now we do that, right? So learning problem would be now to identify W's and V's, right? Dataset D is given, find W and V. Do whatever you want, right? To find W and V. Okay, this is the first attempt, first problem, right? Now, so in 1950s, when people are playing with these things, it goes beyond that, but that's probably the first thing we know is that, okay, how can I solve this problem, right? So here I'm going to present an algorithm. Apologies for making you do math on a Saturday afternoon after lunch. Not my fault. You have to blame the organizers. With the due apologies, and if you fall asleep off, it's okay. I'll awake you when your time comes. Okay, but this would be in a standard textbook thing. And I will tell you what is the thing you should take away. And I thought it's useful to run through the algorithm because of its simplicity. But you should remember that what is the quantum analog of this? So that should be in the back of your mind, right? Okay. Okay. So now the algorithm is like this, right? See, so now you see we made some assumptions. The cats and dogs are there, right? The first assumption we made is that we made a choice, like linear function. Is there a function like that which would classify all dogs and cats correctly? May not be. In such a case, there's no such W to begin with, right? So implicitly made an assumption that yeah, there is such a function to begin with. Whose W value I don't know. Correct? There's an assumption in this. Otherwise, right? So let us say, just for sake of simplicity, let's put B to 0. For simplicity, for the sake of making progress, right? So that means there is a W star which should satisfy all these equations correctly. Existence. Challenge, I don't know it, right? So it's a very nice algorithm. The algorithm is this, right? So that means now, so if you look at this very carefully, sign value is 1 or minus 1. And what is yi is? 1 minus 1. So that means this is exactly equivalent to this constraint, this relationship, right? This number should be positive, right? Okay. So this positive means now if you take the minimum value over the n examples, that must be a positive number. Let us call that number something gamma. Okay. And I just to scale it, I made this right gamma. Right? So there's a real number gamma, positive number gamma, but we satisfy this condition. So that means moment somebody says the linear classifier exists, there's a gamma also comes with you. This gamma has a name. It's called a margin. So the idea is you can see that now if this number were less than 0, what would that mean? That means some of the constraints are getting violated, making mistake, right? So that is the what I want to think about. So gamma is also lots of other connotations, but this is final to start with, right? Now here's the algorithm. The algorithm is this. Let's say you guess a value, you guess a W. You guess a value of W, right? Then what's going to happen? You run through your data set. If this is correct, you're done. Now, obviously, you're not good guessers, right? Obviously, there will be mistakes. So you pick the first mistake you can, right? So let's call the mistake L. So that is that in L, Excel, right? So that is their sign did not match. I run through it, right? Now, what you do, right? WK I have, running through the data set, I picked a point, YL, Excel, whose signs didn't match. That is, it didn't give the right result, right? So in that case, what I should do, you just add that YL Excel. Not just Excel, just add YL Excel to the value. Okay? And if it is, so basically I run through it, and I update the value if I see a mistake. Update is also very simple, right? Yeah. Amazingly simple. Does it work? It does. And it's a pretty powerful result. So let's say, so basically when does it stop? That means when there are no mistakes. Right? So let's go, so that means that if it's a mistake, I update. So now I update. When do you update? I update when there's a mistake. So number of mistakes is equal to number of updates. Right? And so now it can be shown that R is the radius of the radius of each of the vectors. So assume that all the vectors lies in a big ball, right? It's pixel values, how high they can be. So R is that radius, just to say, right? So they're constant. So you see, after 1 by gamma, let's say R is 1 by gamma square updates, the algorithm will stop. It will classify everything correctly. A very simple algorithm. Okay. Easy to implement all kinds of things, right? Okay. Also statistical guarantees, which will also have the number of updates become important, but that is not, maybe that may not be the right, this is not the right place to discuss this right now, because we want to go to the quantum thing very quickly, right? So this is one of the first instances, right? Now, let's ask, like n is like 1 million, so what will you do? How much time will it take? N is like 1 million. Big data world, right? How much time will it take? Update is very small, but every time I guess a value WK, then what should I do? I must scan through the, right? If I'm lucky, the first one is the mistake, right? But the worst case, it would make how many? Each iteration, n calls, right? Roughly. So n r square gamma square is the, n by gamma square is basically the number of oracle calls. We're thinking quantum now. Parallelly, okay, so the parallel can wait. And now there's one other thing. Two ways to solve a problem. Two ways to solve a problem. Throw money at it, parallel. Throw brains at it. Now, people are giving more expensive thing now. People are giving you a quantum computer now. Okay? Mystery. So let's see if we can answer that. Does it, can I do this faster? Okay? This is one of the things you can try, right? Okay? Sure. Now, okay. Now, quick take. So this is gamma. Yes, please. Yeah, if W star exists, it will. Gamma square will stop. If W star exists, if they are linearly separable, it will exist. Now, if, no proof. We can prove it. We can prove it. IISc students and MTech students can't prove this, they don't get a degree. For sure. Right? Yeah. This is standard textbook proof now, I'm saying. Okay? Yeah. So now, but okay. But let's assume we can say that, okay, you proved it, fine. So what? So what is now? We just said, even if this is right, I still have to do how many? N r square by gamma square. That's the time it will take, all clock time. Now, you have a quantum computer at disposal. What can you do? Okay? Right? That is the one thing I want to take you. Now, the next thing is, as you say, so now if you look at this thing, r square by gamma square, no? So I want to think, we should do things fast, right? So what should gamma value be? If gamma is large, I'm done. But gamma is not my control. Gamma is a function of my linear classic data set, right? And W. And the question is, there's not, and now there is not one W. There are many Ws possible. You know, if there is, and you can show there is one, there are many. You can show that. So that means I get a choice of gamma. Now let me choose the best gamma. What is the best gamma now? Maximum gamma, right? So now after all these, this leads to what is known as the large margin classifier. Margin, large margin. And this is also known as support vector machine algorithm. Okay, right? So let's not go into the proof of it. We can discuss it. It's textbook stuff, right? But the point I want to flag is that when you write all of this time, it looks like this. So this is what is known as convex quadratic program. So machine learning is a field which heavily stands on basically three legs. One optimization, one statistics, right? And maybe linear algebra, and of course to some extent algorithms. So this is an instance where optimization is playing a role. Now I have to somebody is told me to give W and B, right? Then I must solve this problem efficiently. This is an instance of a quadratic program. Now to this day and age, quadratic programs can easily solve. Ask MATLAB, you see these quadproc packages exist. Okay. Now complexity. What is the complexity? Complexity, I think I have written something. Okay, maybe it's there somewhere. Okay, but before that, let me make another point that come to the complexity question. Now, in the previous formulation, what you saw was this is greater than equal to 1. All right? See, this is the constraint that I have to satisfy for all examples. That has to be there. Take it on faith that if I do SPM, say this will happen. And so it is what is happening now. You have to remember, you wrote yi w x is greater than 0. That is playing out like this. Fine. Now, there is a variant of the same problem. It will do the same thing. I can replace it by equal to 1. And this is called as least squares SPM. And let us, when people develop this, the idea of developers that maybe this may be, you don't have to use the quadratic programming solver. This may solve easily. Purely from computational point of view. There's nothing more. And one can show if you can solve this, you can solve the other, and this and that. but it's purely a computational view. So why are people bother about computational view? 1990s, 2000. See, there's no merit in solving n equal to 5, 10, nobody cares. N 1 million. D is 10,000. Yes, then you talk. And therein lies the values of these things. That's the thing of task to solve, right? Otherwise, if I go and take an optimize it, they'll laugh at us. Oh, this is all 1950s. Well, because 1950s is fine. But then you ask code doesn't run beyond 100. Oh, like 1 million? Now comes sophisticated science, right? So when I'm saying all this, I'd like to request that, okay, what can quantum offer here? That's the thing we should take away from this discussion. No, mistake is a mistake. Cat and dog, what a mistake. There's no 1 minus 1 there. Cats and dogs, both has to be correct. So the 1 minus 1 doesn't have a play. No. I have to tell you cat or a dog. So just saying 1 minus 1 will not help them. Okay, so now, so maybe this is a thing. Here, those of you going to sleep, I would ask you to wake up and just take note of this. So there is my problem, X is a d-dimension vector, the images. I have given n images of cats and dogs. The complexity of a quadratic programming solver to get epsilon accurate solution is something like this, d cube plus d square n log 1 by epsilon. Okay. So, okay. Now, here is what I want you to think about. On a quantum computer, can I do better? This is what is there, right? Okay. These are things you want to think about, right? Setup is biology explained. Now, how can I do better? That's a question we would like you to ponder about, right? Okay. So now I realize that I have made a very aggressive agenda. How long can I go on? 8 p.m. No, I'm sure they will throw stones at us. Okay. So what I'll do is, yeah. So I will not. Let me just. What I'll do is I will skip some of these things. Maybe I'm just thinking I'm running short of time here. All right, because our key thing is to go to survey. This is not the thing you're here for. You have to, this way you enroll in our courses, right? So you're here for the survey of quantum things, right? So what I'll do is that quickly, not cover most of the like other things I have thought about, and skip some of these. Okay, fine. So we now know. Okay, so the key takeaway at this point is, okay, you have told me 2 algorithms. One is for perceptron, which has a complexity of n by gamma square. Then you told me another algorithm, support vector machine, SVM. Why support vector machine? All that? I'm sorry, we have to 8 p.m. Yeah. Why the name? So it takes the complexity is d cube plus d square n. What is d? Dimension n. Examples. Fine. So let's think like that. And I can solve these problems, right? Okay. Very good. Now, yeah. So maybe because you'll need these notations. So the problem which was earlier can also be solved in a what is known as a dual formulation, where one can think like this. No, there should be one. Yeah. So the original dual of this problem written like this: I alpha j, yi yj. There should be yj missing. Xi transpose xj. Right. Can you see anything? Is there any red dot somewhere? No. Where? Yes. So there's a yj missing here. Apologies for this. But you see this xi transpose xj. Okay. So basically solving the w is equal to solving this. Okay. Why? Then 10 p.m. I'm happy to explain, but then 10 p.m. Right. You don't want to ask now. Right. Now let's say this is also an instance of a quadratic program. Can be solved with the same complexity, but the variables here are alpha i's. Right. And right. Now once you do that, the final classifier would look like, in terms of alphas, would look like something written here. This is my if I write f of x, sine of this, w has disappeared. W is basically the first term. All that. So this is equivalent to the same problem. Okay. Now I wanted to observe the following, right? So both in the optimization problem, the objective, this is called the objective function. In the objective function, how does data enter in the algorithm? What is data? Xi, Ys. It enters as a form of, the vectors enter in the form of this dot product here, right? Xi transpose Xj. To take a decision, give me a new image, I will tell you cat or dog. How does data enter? This is, again, this X transpose Xi. Okay? Now, this is amazing work in physics. People have asked us to think differently. That there are now functions, or the setup now, where I just need access to this dot product. That's all the algorithm will run, no? You do not need Xi, Xj. You need the value of the dot product. That means give me two images, tell me the value. That's all I need, right? Now, implicit in your head is a thing, or many of our heads, but how do I compute it? You need X, you need Xa's, Xi transpose Xj, and then you get this, right? But there are ways to compute that without computing Xj separately. We'll show you this. That's called kernel functions, right? So one example, okay. So now this gives us a way to, what does it immediately does now? It gives us, for example, the kernel function, right? So Xi transpose Xj, we can think like this is like a kernel function, k of Xi comma x, right? And k of x comma x dot is something like a big vector phi x transpose phi x tilde. Right? Now, for your algorithm to work, you don't need phi. You need k. Now the interesting thing is, are there k's for which I can compute k of x comma x tilde without computing phi x? Okay. So now, I hope some examples. Okay, see, these are lots of fancy theories which I skipped now. So, for example, this last one, no? Where is that dot? Okay, I'm sorry, I can't see the dot. So see, this is an example of a kernel. This is a kernel function, right? But the phi x is not, phi x is a very high dimension thing. I don't need to know that. So this is an example of a kernel function which satisfies the dot product criteria. I'm sorry, I skipped a few things, So basically, k of x comma z is something like dot product of two big vectors. And now, it is not always needed to compute the two vectors explicitly and compute the dot product. And that's kernel function offers us. So this is all comes from reproducing kernel Hilbert spaces and all kinds of other theories, right? So for example, this Gaussian kernel is the d power minus half to sigma x minus z square, right? So basically, there's a theory, let us say, that I can compute those k of x comma z explicitly. What does it do? At one go, what is the algorithmic cost? Algorithm cost doesn't change. But it immediately transports me to work on nonlinear things. My computation cost is same. MATLAB is the same thing. Same problem. Okay? This is the bill of thought. So this is the elegant math coming on this, right? Now, one is, so my computation cost, does it increase? No. Computation cost doesn't change. Computation cost remains the same. But my ability to model more complicated things increase at one go. Okay? Right? So these are some, so basically, so this is one of the ideas, right? Again, like you should say, oh, fine, this is very good things, great, but I'm interested in quantum computing. What does it mean? Right? These are things I want you to raise questions, right? Okay. Okay. So now what I will do is now, good. Okay. So the least squares setup, no, we saw earlier, right? Now, I'm sorry I couldn't spend much time, but end of the day, it is something like Ax equal to B in a set of equations. That is where you equality is, right? A is a constant matrix. Z is your variables to solve this. Given A and Z, right? So, especially in machine learning and many engineering fields, your ability to do things depends on ability to solve these things. Where let's say it's a D dimension, D cross D, there are large D's. That's what governs most engineering solutions. Okay. Now that's why it's very important. Now the vanilla method, Gaussian, this and that, right? You know the complexity is DQ. Now you see, obviously, then why in this day and age, if you're writing Ax equal to B and claiming something, the problem is like 1 million is not going to be useful. I'm using million as a way to illustrate the point that it is computationally it can get solvers will not give it meaningful time, right? Now, herein lies merit in sophisticated algorithms from optimization. One of the methods is called conjugate gradient. Those who do not know, want to look this up. So conjugate gradient can solve the problem in order d square kappa, where kappa is called the condition number. What is the condition number? The ratio of the largest to the smallest eigenvalue of the matrix. Assume for now, without lock, I will say that A is a square matrix, square PD matrix, positive definite matrix, right? So all eigenvalues are positive. Okay. Now you can do better. You can do better. Now suppose you know the following structure, that most of the elements in A are 0. Let's call them S parts, that each row, the number of elements, at most S of them are non-zero, rest is 0. Okay. So then you can show, of course, you have to do like, so basically it's like ds into kappa. So these results we have. Now I've already made a pitch that look, if you can solve this, you can solve many things. What can quantum do here? Right? So these are things I would like you to think about, right? Okay, that's great. 3:10. I'm looking at a watch. Okay. Okay. So now let me do one thing. So the unsupervised learning part, I have to wait now. So, yes. Huh? What are you supposed to give me? Z. What is the inversion in this? What does inversion mean? What do you have to give me? D square numbers. Z is D numbers. All this is very important. All this is very, very important. If you are hold me to inversion, I have to give you D square numbers. Right? But I am only held to Z, D numbers, so to produce for you. And make an argument that is close. Of course, there's a hidden is epsilon close and things like that, right? And this is very, very important understanding. Okay, now I'm serious enough, and also I think, also I will ditch the unsupervised learning part, and let us go to the survey part. Well, that's what we are interested in, right? I already made enough thing about this, so now let me see. I'll require your help, please. Yeah. Maybe we should remove this. Yeah. Great. This time I'll work first. Yeah. So the unsupervised learning primitives, we said we will park this side, and let's get back to the. I think we have already enough questions to discuss now. Right? What did you have now? Perceptron, SVM, solving A is equal to B. Okay? Simple things. I mean, what you're doing? Right? Okay, just if you think these are too simple, don't blame me. People are writing papers on this now, and good people. So, okay. So now, so let's go to the survey of quantum analogs, right? Right. So Grover's algorithm. Okay, so as I said, my learning, my understanding of quantum is limited, but this is the only algorithm we will do. Other primitives I will ask you to copy. Maybe you know more than me. So the Grover's algorithm now, the way we learned it, or the way it was posed as an application problem, the given database of fruits. One of them is rotten. How do you find it? Okay, so what do you have? Your oracle tester. You know, the tester tests and says, this is good and this is bad. Okay. Now classically, if the like unsmart people like us to test, what will take? So the worst case is and test all the fruit, and by the time you don't even know your tongue is responding to right things or not, right? Or you get lucky the next one. Okay. On an average n by 2. Roughly. And you know, Grover came and made this thing. Okay. Now let's put them in a Hilbert space. And then there's a superposition of states, all these things. And then you can think about make an operator now, this operator, oracle operator, which takes in x and gives you minus x. Right? If x is rotten, right? And if it's not rotten, give that, right? So the question is now I have to take my objects and put it in a Hilbert space. Kernel functions are dot products in a Hilbert space. Okay. Unnecessary observation, but anyway, some observation. Okay. So now you can see what does the Grover's algorithm do now? Now you know the proofs very well, right? So it's order root n with high probability, will tell you this. And where does the magic come from? Where does the order root n come from? The ability to store data in a superposition of states. That's the physics part of it. Right? If you can store like this, the physics was telling you that okay, there's a mechanism to do that. If you can do that, okay, we do amplitude, there's amplitude amplification and things like that, and get to this. But those are names, fancy names, but the algorithm is very simple, right? Okay, so we take this as a description of Grover. So what can we do about this? Any guesses? Fruit, rotten, one rotten. Any guesses? No, go to the context we're discussing. Of course, this is very powerful. Which context? So where do you think it's going to be applied? Where do you think? Which step? Barcelona already told you. Barcelona already told you, right? So that's a very nice work. This Wiebe, Ashish Kapoor is one of these things. This has two ideas in this paper, but it's the first idea. This is, I think, I don't know, 2016. This is 2016. NIRFS is one of those big conferences in our area. Okay. Now you can imagine what the magic is. The magic is that you try to make a case that they call version space, that you store quote unquote. What is now? Can you tell me what phi1 through phi are? Any data points, right? Phi1 through phi are all the data points stored in the Hilbert space. Now just repeat that process. Just it. Okay. And now how many oracle calls? Root n by gamma square. Root n comes from where? Grover. Right. See, these are things. But this is just beginning to happen. Was in 1950s, right? It's beginning to happen. Right? Of course, there's one more idea in the same paper, which you don't want to discuss. But anyway, this is a good, interesting thing, right? Okay, this is one of these things. I would definitely request you to look this up if that's interesting. And I'm sure many things have happened beyond Grover. So you can think. They're in a very nice paper, by the way. Right? So amplification, the basis of Grover, right? I think that has many, many uses, not only machine learning, but any other fields, but love to know more about how things go. Okay, first application, right? Okay, so 1.3.17. Okay. Yeah. Next. So yeah, so this somehow, when I talk to colleagues, this is something I don't hear. But to me, this is one of the most remarkable things than Grover. Because this is the thing I get faced every day, my day job. End of the day, do whatever you want, but A is equal to B, I have to solve. Large. And this is the first attempt I see. This is HHL algorithm. This three thing. This is, I think, is according to me, this is more important than Grover. Of course, the way of saying it. So this is, so what does HHL algorithm do? So this is probably at that point that didn't. This is 2009. I don't know how many of you are aware of this, but if you're aware, you probably know. I don't know if you're aware. I would definitely ask you to look this up. More than Grover. That's irrelevant talk, but anyway, good. Thanks. So it's the champion. Everybody should know. Everybody should break this algorithm apart. It's as powerful as this. So now, what did you actually show? Right? And there is, so basically, and this point, this algorithm, 2009, right? They didn't have all those fancy machines now, which we showed, right? These are breaking news to the 1000 qubit, this, that, right? So this, obviously, so what is it? Okay, so again, I don't like the bra and kid notation. To me, they are vectors. That's the way I understand it. And so those of you feel a little challenged by that, please feel free to curse me, but it's easy for me to understand. So the idea is, first, this thing you see, state preparation and all that. So now, so the way to do that is, or think about it like this, that take the matrix D cross D matrix, and what do? Linear algebra, spectral representation of A, lambda UI transpose, first course linear algebra. If you don't get the answer right, no chance of getting a pass grade in that course, no? So the first theorem, lambda UI transpose. What are lambda is? Eigenvalues, UIs are unit vectors, eigenvalues, unit length. Okay. Now think like this, state preparation means that you have the UIs and they are stored somewhere in your states. That in, then you put the kets. UIs are stored this, right? Okay. Now you represent B in the same basis. Those are registers now. B gets locked in, BIs gets locked in. So B is now D numbers. Locked in. That's, so basically it is B as represented in this. This is not ith coordinate of B, by the way. This is, so basically this is B transpose UI is the BI. This is not ith coordinate of BI. UI are, the basic UI bases are not the standard basis. It's eigenvector basis. So B transpose UI is BI, right? Just to be clear. Now you see, I have to output for you what? X equal to B, I have to give you X. So now the claim is, now in this quantum state, basically you need to compute this BI by lambda I values. What is the inverse of A? If UIs are known, what is the inverse of that? 1 by lambda I, right? Can I think about an algorithm in quantum where these things have been done? Where I know, where the need is, I am given the eigenvector, but somebody asked me to compute the eigenvalue. Quantum phase estimation. Kitaev. The operator is there, those unitary operators, right? And so there are things we looked up, no? Those of you, right? Now the question is, the HHL algorithm produces for me an output, approximate output, epsilon correct with time complexity kappa square s log n by epsilon. What is kappa? The condition number, you know that. So why is it exciting? What is exciting about this? Of course, depending who gets excited by what, but young people may not be excited by this. Look at n. Look at n. Log of n. Log of n. That was k into n. N is like 1 million. That is the magic of this. But nothing comes free. Nothing comes free. Now you have to ask, okay, great, good. No, I can't give you X still. But, this comes a lot of buts. That means, but the result is that suppose I give you another operator M, and suppose somebody asks you to compute X transpose MX with solution of this, I can give that number very easily. So this is taken with a pinch of salt. Okay? Right? So Basically, what I'm saying is, I have distilled for you the key result, the complex result. So what is the exciting part of it? Log part, log n, million, immediately, right? But it comes with a lot of conditions. It's not as simple as I can just take tilde. But it has its own uses. Right? So that's why I think is the most important result, right? Yeah. Now, so what is S? Again, what is S? Sparsity. The same thing we talked about, right? Right? Okay. Right. Right. So now, first application. See, after HHL paper came out, there are lots of applications. I'm sure a lot of very good citations. Because if you can solve AX squared, we can solve metrics. And that's what you will see citations with. The first paper which I would like you to, recommend reading in this case. So as you can see, so now remember the question was inverse. Inverse means you have to give it d square numbers. They are not. And here they don't even give x tilde also. They will say that, look, what we'll do with x tilde? X tilde is often not used in isolation for something. And this thing happens in machine learning a lot. In kernel methods and all that stuff, right? So that's what it is. So now basically, as you can show, it's possible inverse basically, right? And now this again, Wiebe, the person who developed that perceptron app, what is data fitting, by the way? Ax minus b, same thing. Started with Carl Friedrich Gauss. We are still there, right? So now, that's why the least squares problem. So again, you can see we apply this algorithm. This is there. Log n. Thing is, this gets a little what? Epsilon close and all that, right? Now the modern research is, can you cut down? This is the biggest part, biggest win. Of course, we come up with lots of things, epsilon cube, all that. So now can you make epsilon better, this and that, right? So there are lots of very, very good papers coming out now. How to distill this, right? So amongst the papers which I want you to read is this one. I'm sorry, I should take back, not I want you to read. You read whatever you want. The same. This is the most recommended one. So now the key result was this. Key result was what? No. Log n is 1. But then the S. When can I apply? KS, right? So they present the algorithm when the algorithm was sparse. Sorry, the matrix was sparse. What if the matrix is dense? Dense is then you will see won't get S. If the big n log n, the n will show up now. Because I have to now. There's no way I have to read the data once, right? I can't get away from this. Now here comes the magic. Anupam Prakash, root n there. This is the root n. So this is the magic now, right? So that's why I think this is a very important. I would say there are lots of good, progress, but this one I think this is one of the biggest progress to pick one. Now, okay, now, so this is our first level of ideas, right? Now the second level of ideas, like this. Now let me present another set of ideas, which frankly I don't understand at all. But maybe there are people here who know better, and then I will say the ramification of it. So the idea is this: there is this proposition of QRAM, right? So this quantum random access memory, right? So what do they say? The paper is very nice, calls it bucket brigade, like buckets are things up there. And they try to mimic the standard computer architecture where you store things in a register. And now the main story is, of course, you require, suppose I want to say that I have to store vectors of d dimensions. I look at ND register, I have to store that. There's no getting away from these things. But the magic is to access is log dn. I want to figure out which one is rotten. Log dn. So don't have to parse through all the dn things. This is the magic. But this is, to the best of my knowledge, this is a fantastic idea. I am not aware of any actual implementations of this. Now this is where I was thinking that many of you may know more what has happened here. But now, See, if you give me a system like that, I can exploit it in many ways. And that's some idea I'm going to present some of these things, right? Yeah? Okay. So first thing is, so now you see PCI skipped, PCI came back here. So yeah, Seth Lloyd's group has done amazing work on some of the generating some of these great ideas. So this is the title of this is this cut paste of the paper's title, right? Calls it quantum PCA. So what it does is, so it's another interesting thing for, so what are the, yeah, this hopefully will come later. So in machine learning, or even you talk to statisticians, we are used to thinking data or thinking in the probability distributions. But in quantum, that is not enough. You have to understand what are called density matrices, right? And there are many uses for that. Now, one of the leap of faith this paper makes is that they request us to look at the density matrix as some sort of a covariance matrix. Okay, right? Now, PCA, principal component analysis, suggests for a low-dimensional manifold by projecting data on the eigenvectors of corresponding to the largest eigenvalue of the covariance matrix. I'm sorry I skipped that part, but just take this definition of PCA. He said that if you try and do that, then, so often this density matrices doesn't stand in isolation. People do some things with it, right? I said whatever you want to do. Now the thing is, often what happens is the way it is, so like again, recall a definition of density matrices. You want to extract probabilities out of it. How do you do that? You compute eigenvalues. Those are probabilities. That's why the eigenvalues are very, very, like some of them are very large, some of them are very small. Okay? Most of them are very small, let us say. That means we have a few large ones that should do. And that's exactly what, PCA works best. So you said if you appeal to that picture, then I should be able to compute using QRAM things very quickly. And more importantly, what is important is in many applications, for example, when you want to run your Toyota Suzuki and things like that, what do you do? E power I rho. So the exponential the matrix. So that can be done in log D times. Assuming I have QRAM access. Right? And implicit statement is that works best when the number of eigenvalues of the density matrix, right? The number of eigenvalues which are very large are very small. So that is, some density matrix is there. There are, let's say, D is like 100. There are 5 eigenvalues which are like, 0.1, 0.2, 0.3, and rest are all roughly 0. But this is the case. This will super duper, nothing, assuming Q RAM, right? And then he goes on to say that it has a uses in quantum phase estimation and self-tomography. Those are probably as a very important in quantum computing perspective, but this is what one of the things is, right? Okay. Next idea. Said that when I say vector machine, this comes back now. Support vector machine now. The same idea now. Suppose I have QRAM access. So what is it? We already saw the complexity of linear SVM, right? It is ordered D cube, log n, and all that. We wrote down. That's a classical hardware. Now the thing is, if you have, so what will change now? What will change? What does QRAM do? Huh? But what is the thing? Storage remains same. What is the thing you get? Access. So log n. Right? Log n. Now this is amazing if this can happen. This is amazing if this is actually realizable. Right? And just like your exponentiation and things, there are also applications in machine learning where you want to exponentiate a kernel matrix and things like that. There are also such things, same ideas can be borrowed, right? Now, if you want to make it nonlinear, that means you use it for a favorite kernel function. One kernel function already showed polynomial kernels, right? Now, again, because it's log n, you can very quickly compute those dot products very quickly in R log n terms. So these are all these nice things which can be facilitated by our QRAM access, right? Okay, I'm not taking a watch in my right. Now related reading. So as I said, that now you can see the why I wanted to do regression and all that, right? So I definitely request you to read, and I not read whatever you should, whatever you like, but Anupam's thesis, excellent example, very well written. All the proofs are there, and he takes on QRAM and walks us through all the proofs. I mean, okay, I didn't work out all the proofs, but some of them, but I really liked it. Very, very pedagogical. His paper is also very a joy to read. So there, especially chapter 3, 4, 5, but the 5 is machine learning algorithms. So he talks about the ridge regression and how to make it better, this and that, right? All this, but assuming QRAM access. Okay. Now one other paper I did not put here is, again, it came out in ICML, maybe, I don't know, 5, 6 years ago. So he then talks about k-means algorithm. EM algorithm and k-means algorithm, but that's different, but the same assuming QRAM access. Okay. Yeah. So this is all the things, if you wish, you can do. But now comes the bit of a rub. That sign stands for caution. So now, as you can see, because of A, technical challenge, B, lot of industrial interest, the reason for solving Ax equal to B easily, and compute eigenvalues, for example, of a large matrices. Okay. Now there's a lot of literature on the following, especially for PCA. PCA is what? What did I say PCA was? PCA was that finding the largest eigenvector, finding the eigenvector of the largest eigenvalue of the covariance matrix. Right? That's PCA. Now, question. I have 1 million data points. 1 million way of thinking that it will not store, that I cannot use standard algorithms. It will not even fit in my memory. If you have memory for 1 million, just take me to 100 million. So it just doesn't fit. That's the way of speaking. How will I compute this MPC? So people have thought about the following. Okay. In your memory, you can store only 100. Great. What do? You pick 100 examples whose norm, the vector length, is large. Okay, and that can remember one pass over the data. I make one pass of the data, I can give you the norms of the vectors, no? Then I can sort them with one pass. Right? So pick 100. Why 100? 100 is what you can store, right? And that I can solve. And now I can show you that would be pretty close to this. Okay, all this when I say this is not just hand waving, that we can write down theorems. I'm hand waving now, but there are theorems, like one paragraph long theorems are there. So this is sometimes called length square sampling. Why length square? The largest norm, length. So this lady, Hawin Tang, she says that she tries to prove that all the speedups you are saying, log and all that, QRAM access, if you stare closely, basically the length square sampling is happening. There's no magic. Because your assumption of state preparedness is coming in play. That's the thing. But so I think it's very good to read all these papers together. Then we can analyze them. This just to put that, see, like there has to be healthy skepticism for anything. Right? It's only healthy skepticism. Right? Sort of. Right. Yeah, this is another paper. A lot more has happened after this, right? Okay. So 337. 337. Okay. So maybe, I understand just the quantum part, right? What are things you've already seen, right? So far, this, okay, if QRAM is there, it enables powerful algorithms, especially in the big data setting, definitely. If that is the thing, already ideas are coming out, and maybe we can, and I would love to apply my mind to more such things, right? And this is, so, but, Now you see what does HHL give you exactly? Let's start to HHL. What does it exactly give you? So two ideas, right? One is QRAM, all these things. HHL is one more algorithm, right? What does HHL give you? If you think like this, it did not give you exactly x equal to b. It didn't give you that x. It gave you an approximation of x, number one. Number two, and it says that, okay, that also will not give you. But if you want to take that x and compute something in a quadratic form, that number I'll give you. Right? That's the thing which is, of course, it's a very big paper, all kinds of things, but that's the summary of it. Right? Now, so now here is something I want to see, for example, the difference in machine learning also does optimization, right? You take a mechanical engineering colleague, they also do optimization. You talk civil engineering, they also do optimization. And you talk to an optimization expert, they also do many things, right? But the difference is this. A simple way to put it. Same code runs. Conjugate gradient, conjugate gradient. Now ask, when do you stop? When does the code end? You will see herein lies the difference. See, GPUs are there, right? Now ask any high performance computing expert, GPU will start cursing it. Machine learning, the objective function which you set up. See, finally, what will be I held to? I to build a machine. Nobody cares about solving my SPM problem exactly. I'll be held to, next time I show an image, you better get it correct. That's all I'll be held to. So the objective function exactly is a very poor proxy of that command. So by and large, if you can solve it very, very approximately, it's fine. So that is when the machine learning expert will solve the conjugate gradient problem for the problems. The stopping condition is very loose. Whereas if you talk to any civil engineering or mechanical engineering, they'll say, no, 10 power minus 6 should be the epsilon. Because the demand is like that. A bridge will fall down. Right? But now to say there were cats and dogs, maybe I don't have to solve this exactly. First the decimal is good enough. And that is exactly the opportunity this field provides. But that is what I'm seeing from reading these things, right? So I wanted to share this thought just to make sure this is where you want to see where QML can grow. See if that resonates with your understanding of things, right? Okay. Yeah. So also there is one more interesting thing that struck me. This quantum PCA, right? I don't really understand why he has to think the density matrix has to be a covariance matrix. In machine learning, there's a lot of interest in other fields as well. What is called as low rank approximation, covariance or otherwise. You give me a matrix, I have to make a low rank approximation. A lot of tools and techniques and things like that. And this is exactly what the argument in the paper seems to be. So I did not see any extra merit. Maybe I missed something. So when you look at the papers, you're going to see that, okay, what did he miss? Why can I not say it's just a low rank approximation? Why did you appeal the density matrix via covariance matrix, right? So things like this. But if low rank matrix is a thing, there are lots of good tools which we can borrow. And then if tomography if need tomography, great, right? Yeah. So some of now, no, not over yet. Okay. So now, okay. So the next big thing. So we talked about some of these things, right? Now the next big thing, which is actually happening today, is what is known as PQC, parameterized quantum circuits. So the idea is now. So this kind of pictures is there. So this I would recommend those of you who already do not know about this and want to get a good introduction, I can recommend this paper. I'm sure there are better papers, but this is my recommendation. It's 2019, but still gets you the first basics and more progress can happen. So what does it do? So you have your data. What is the data now? Images, right? Now the thing is I have to feed it to a quantum computer. What should I do? So to load it in somewhere, all those. So all the signs mean a lot of things. So this is a direct sum, this O, the tensor product of O's and all that. So you know all these things, what it means, right? Now U of phi would be some sort of a data loader kind of thing. Okay. Now there is this another. So why is U? Unitary, because that's where you want to code things up, right? These are comes from the notion of variational circuits, right? Now, So that's the data loader circuit, and this would be basically the standard model. And then what you do is after that, this goes into a quantum computer, this is the circuits, and after that, this is the measurement procedure. Once the measurement comes, you then compute a function on it, and then you say, oh, here's my classifier, and things like that, right? This is the post-processing part. This is basically the idea. Now the question is, so what are the parameters now? So just like W's and the B's, what goes inside the unitaries? Those are my trainable parameters. That is where a lot of good excitement is there in the field now on what can I do with this, how can I train better, things like that. So as I said, I will not be able to, I will not cover the applications of it, and of course, which is a very good thing. But our goal is to see technically how, what are the challenges here, right? Okay, so now, not a good idea, right? To call this now, no, or ditch, it's math. So the point is that you probably know this polygates and Hadamard gate and things like that, right? So now this goes into design of those circuits, right? So now this U5. So basically, how do I look at it? Now, machine learning is a field like this, right? It runs on excellent codes written on linear algebra. Then unless I have to think matrices, think vectors, I can't do anything. But that's the tools I know, right? So when I look at the circuits now, one way to look at it, you can also parallelly track, oh, these are the matrices being multiplied to, and that will help develop algorithms, right? So now, for example, this is I think probably this is in the terms of flow of things. First is the Hadamard gate. Suppose there are 4 inputs, there are only 4 pixel values, for example. Now these RZs are some special matrices which you saw the last time, right? And theta 0, theta 3 are my, let us say, the parameters. This is an example of a circuit, right? Now, so what is the challenge? Again, I did not complete my neural network kind of thing. So where the challenge was this, right? That the learning progresses in a traditional neural network kind of thing. There's objective function, and you want to make objective function lower. And the algorithm to do this is called gradient descent. That is what you do is you have a particular value of theta, and now that's my objective function L. You pick the new theta so that it is along the direction of the negative of the gradient, right? And the question is, what is alpha t? All that. That's some science to it. But the challenge here in this case is, so first, for whatever reason, people identified it as a neural network, which is not. It's just a collection of circuits. But the interesting thing is, why the sum of the things will carry over is, I suppose, that in neural network also you see output here. Now that output, oh, this is not a cat. Oh, then I made a mistake. So you want to propagate back this thing, and that comes in the derivative. So this is something called back propagation. Now that is the principle people are using here. The challenge. So just to be clear, what are the parameters now? Parameters is u theta, and what is u? E power minus r theta, all that, right? Now, this should be done extremely carefully. E power minus t. If I have to compute this every time, like t is like 5, you can get some number, t at 10, almost you're done. 0. And some of these problems come and hit you back here. So, and that's what people see. So people often say that gradients have no information almost. It's almost like 0. So there are more, I'll skip this also, but I'll point this paper, these 2 papers here. So something called Baden plateau problem. So as you say that going to back propagation, that's that gradient value is often 0. That means I'm not updating anything. Right now, this probably requires serious rethinking. So now, what it turns out is that so this was I mean, of course, there are a lot of papers that pointed this out, but if you ask me to pick one paper to read, I'll pick this paper. So there, they first make this observation that because of this circuits thing, and especially circuits is the unitaries and all that, by and large, on the average, the gradient is roughly going to be the 0. Basically the function roughly becomes a constant. The variance of the function is 0. Variance of the function goes to 0 as number of qubits increase. So this is one of the diagrams if you want to see. Here is, so let us say, okay, what is u of theta? You have this block sphere, right? One of the things are happening in some sort of a sphere. Okay, while that is not the picture here, but just to understand that, right? Now, say as I changing theta now, and theta is unitary and all that's affecting it, so there'll be some band, right? Now there is some theorem, and you can goes back to concentration of measured phenomena, can be attributed to Levy, some very deep science, and they say that the function value would roughly remain the same. The epsilon will go down as number of qubits going to see. It's more of a conjecture at this point, but there is some systematic backing of this, right? So this immediately suggests two things. One is obvious. Neural training is what you just, now the codes are so good, you just throw at any starting point, there are a lot of good codes happen, and something will give you a good result. This is not that kind. So you have to be careful where you start that algorithm from, when it's theta 0, what is the initial point, right? And that's what this paper proposes. But this paper, the way it is hinting, I think the circuit itself looks like a bad idea to begin with. You need to rethink the PQC kind of procedure here, right? Because if you can't train, what can we do? Anyway, so this is an invitation for you to dig deeper on some of these things, right? Okay. Now, okay. So now there are other things. Okay. Now in the remaining 10 minutes, what I will do is I will switch track and talk about some research we are doing in our group, right, to alleviate some of these problems. We have no clue how to solve these problems. Okay, we'll do something else. But I'm sure the smart people here who can solve some of these problems, right? Okay, but as you can see, it's rife with very high quality problems. I just given you a sprinkling, and I can share the whole slide deck with you. There are other things which I couldn't cover. Okay, so now let us now check the first thing: challenges in PQC. Right? So this is so Shayantan is one of the leading this thing. This is the Baden-Platter problem we already saw. What's the Baden-Platter problem? That the gradient is 0. The gradient is 0, I can't update. I can't use gradient descent. Okay. Now there is this slide I just quickly went over. So even then, sometimes, but whatever it is, sometimes the gradient evaluation, it can be done elegantly, what is known as the parameter shift rule, right? So let us say, even if we get lucky, that is, the gradient has some value. Even then, it is not easy. Why? To get the gradient, I have to now run the circuit many times. And where is the quantum computer located? At IISc. Do you have a quantum computer? No. Where is it? AWS, Microsoft, and what do they do? Give me money. Give me money. Everyone on a circuit, give me money. Now, so obviously the most, that means, but I have to model cats and dogs. I have to now spend a lot of money, right? So there's a number of circuit evaluations. The challenge. Now the question is, you forget the Baden-Platter problem, but even if it runs, it's still not that simple to run, right? Sort of, because it's 2D circuit evaluation. Right? So what can we do? So okay, so as you can see, Shayantan came up with this number. Anyway, so just the point I think is made. So now so here is some methodological thing. So now there are classic optimization frameworks which are underused in quantum. So now when you gradient descent, that is called first order optimization, because first order means I have the gradient with me. Now there are algorithms which are called direct search, that I don't have the gradient, still tell me how to minimize it. These are called direct search method, right? So make some progress to that end, so that the question is that can I minimize the time? I don't have to evaluate circuits. So what I do is, randomly what I do is, okay, I suppose I've got to a guess theta. Now what you do is, you randomly generate a vector v, let's say Gaussian and all that, right? Now you add the vector v to theta, subtract the vector 2. So basically 3 points now, theta t plus v and theta t plus minus v. Evaluate the function value at 3 points. Which was lower, go down the direction. What did I do? 3 circuit evaluations. Right? Now, does it work? Now, yeah, so now here it lies, now to prove things. So now you can show that this is, you can do it in, like, those are all results. Right? So this is how that, so the reason for pointing this out is, I think this kinds of exciting and interesting. This holds to science. Yeah, and maybe also will energize people who think about these things in the quantum community to think about other things, right? Now, next problem. Yeah. Okay. Yeah, screw table is coming up. We'll show this now. Yeah. So there's next problem. The kernel functions we said, right? So now, parallel to this idea of PQC, there is this very interesting idea came out. Maria Schuld, she was trying to propagate this. So what, so it says is the following, right? You take your data and just like the kernel thing, you try to represent data through a density matrix, the rho of x, right? And now pretend that the rho of x is basically the feature function. Now, if I open my mind to that, then all it takes is I can now borrow kernel machine as is and do things, right? And where I bypass completely, if not almost, the PQC related challenge. Okay. And now to do that, I'll need some gates. For example, in the same this paper, you will see these swap gates are needed, to do some of those things. But now here, so what is the challenge here now? So there are 2 kinds of gates now. Now in this case, so basically let's not ask how, but let us say I give an x, I can compute a density matrix for me. That's my feature vector. It's not a vector, it's a density matrix, which you know very well. Now given 2 density matrices, I have a computing measure of similarity. Let's take the trace of this. Great. That's the math. Okay. Now what do I measure? What do I measure? Measures only coin toss. Each kernel functions, right? You have to be basically an expectation of a observable. That means what to get, but the algorithm to work, I need the k value, the kernel function value exactly. The challenge is now, how many coin tosses will I do to get this? Huh? Yeah, it's overlap. Here's the thing. But the question is, how do I measure the value? So what is that? What is that expression? Trace of rho. How will you compute that? How will I compute it? What is the value of it? How will I compute the overlap? So what you'll do is you'll do experiment. It's estimate. You estimate that, right? How do you estimate that? Not estimate. Is that value overlap? Well, what code will you run to give me the value? I want the value. Basically, what you'll do estimation. The k is 0 or 1, 1,000 times, 0.9. Right? And now this is said, right? After this, so this is picked up. Now the question is that if you go and look at the papers, there's something like, so I want repeatability, right? Because reputable is not science. Now 50,000 things for getting one kernel, one estimate. So k value is like 0.9. How to get a 0.9? I will toss a coin 10,000 times. Hopefully 9,000 times it will be 1. And 1,000 times it will be 1, so I'll say 0.9. But I can't do it with 10 tosses. Every toss you pay a money to IBM. There's nowhere to good science. There's no good technology like this. So now we see the challenge here, right? All this is very nice to know. Look, it comes with this problem. That comes with this problem, right? So this number of measurements, right? So essentially, there's another more interesting thing we observed, which is probably not here. Yeah, okay. So I think I convinced you that the kernel method is great, but probably it suffers from this, number of measurements, right? But there's one more interesting thing. It's not here. Okay. That's why I called it reliability. Now, there are lots of good results available in the web papers, right? Just do one thing. Take their code and start to run it. You will see on Monday it gives a different result, Tuesday it gives a different result. Why? Because they did not tell you the number of samples. They would experiment again, we will get the same result. So they're all unreliable. We checked it. Because the number of samples matter, right? The K value is wrong, then everything is wrong. And maybe the day we reported on that day, it was lucky. Same result, we will not get it tomorrow. We have to do far more experiments, right? Then they never report the error bar for that. So this sets up the problem now. As I said, I try to map it in a very interesting way that every time you toss a coin, you make a measurement, you have to pay IBM 1 rupee. So what is it you have now? You have a budget. Now give me reliably the classifier with this budget that only allows so many measurements. Okay? Clear the problem statement? Now, okay, so now here comes, that's a reliability. So we did some literature on this. So now I'm excited about optimization. So there is something called probabilistic optimization, chance constant programming and things like that. So that can make entry here. So basically take a software machine, the kernel formulation, and ask that, okay, if I have the kernel values approximately known, what can I do? So this is a nice optimization. So this is basically, so here you see this is a good playground for optimization, statistics, and probability theory coming in play. But anyway, those are fancy math. But okay, finally, what code do you have? Okay, we can check. We can beat them. We think we can beat them, but good to say. But maybe you can take a look at this draft here, still archive, and point out mistakes here. Welcome. We are still developing it. Okay, so this has some of this. Short frugal. What is short now? The number of shots are fixed. Measurements. Frugal. They have budget on it, right? Now what can you do to this? But your classifier must, whatever result you give, must stay the same. Yeah, that's the challenging problem, if you will. Okay. So now it's already 4 o'clock. Can I get 5 minutes? Okay, with all of you, 5 minutes. I'm sorry, I'll hold you on something more exciting, I'm sure. But okay. So here is something. Okay, this really I'm excited about. Okay. So now, remember the images I showed you? The cats and the human faces and the MNIST and all that, right? Now we found that no, as I said, all these are different direction, right? But you couldn't find no algorithms which can actually do this. So now I gave you this flavor that Boltzmann machine was inspired by what is called as Ising model of magnetism, right? Now there is also a quantum version of that Ising model. Those of you who have physics background will know this. The thing is that what you have to do is to direct magnetic field. Field is the language they speak. Is like a force, right? Now in a standard setup, the fields are in the same plane. But if you put transverse field in of force, that would be the quantum Ising model, right? Now, question we ask is that if you replace, so the since I did not go through the Boltzmann machine in detail, Boltzmann machine can be thought about as Ising models we already spoke about. What is Ising model now? These are basically spins, ones and minus ones. Okay. Now in the Boltzmann machine setup, the idea is this: that thing there is an image, black and white image, ones minus ones. Okay. Now if I show you many images of, let's say, cat or a dog or a human, you can very soon guess. No, suppose I tell you, if I show you eyelashes, there should be something like eye coming here. The structure that would be caught in the interaction weights between the Ising model lattices. That's the Boltzmann machine's magic. Okay, I'm simplifying too much, but that's basically the idea. Now, and that is the way it is operated. The mathematics of it. You take the Ising model thing, and now when you want to operate it, you will say that, oh, I fix the first one, I tell you the pixel value, the first one, the first pixel, second pixel, fifth pixel, 10th pixel. Those values are 1, -1, all that. Guess the rest. That's the problem both of us try to solve, right? Now the question one can ask is, inspired by the quantum Boltzmann, and that can do what? That can do MNIST and all that. Of course, a variant of that, R-restricted Boltzmann machine. The question I ask is, okay, now take the transverse field IISc model. Why are you doing this? Because somebody said quantum is coming and this is a big thing, big thing. So what I do is replace the bits by qubits. And all math just breaks down completely. Because this is now density matrices and not probability distributions. And ML people are very, they are not that smart. They haven't figured out how to do density matrices. And that is where we are in this semester, right? So, I heard a word before, the density matrix. What is the density matrix? Density matrix D square. So there is another thing called D plus 1 anywhere, but the thing is the fact that the D square thing actually kills everything. As I said, I have to develop for you running code. I'm not happy with saying, oh, this will be done. Show me that image, generate an image. And for that, I need running code. And the code cannot ingest something like matrices. It's just not a linear algebraic thing. Because fundamental rethinking of mathematics and the things which we know, right? Some sort of thing, right? Now, but okay, long story short, challenge problem is this, no? Can you do this? Okay, existing result, a density operator, no, I'm sorry, 5 minutes density would have very bad idea, right? So let me see what others can do. Okay, we didn't think about QBM. It's not we invented QBM, we have nothing to do, okay, wasting time, QBM. No, others have thought about this. And what if they can do is, all kinds of things, does not care beyond 12. Why? 12, so basically, if suppose the Boltzmann machine has 1 bit, what is the information? 2 states, right? 2 bit, how many states? 4. 2 to the power 10? 1000. 2 to the power 12? What's the challenge here now? In that case, I have an energy function, the value I can create, right? Here, I have to populate for you 2 to the power 12 information. It's a matrix. And therein lies all things got breakdown. And that's why they cannot go in 12 physical numbers. Okay? Right? So this is, I think, is a new opportunity. I'm going to use density operator, let's favorite models. When I say no algorithms, I'm saying algorithms which can work for those kind of problems that make it competitive with RBM. Right? Absolutely 12. And what is the, how many, so now MNIST, that's the MNIST data set, the images, right? There are 784 pixels. 12. Okay, so long story short, the fact I'm saying this means we have done something, no? So this is, we have generated a QBM with EM algorithm, and this is exactly the match. Now to do that, we have to reinvent this EM algorithm from scratch. And then we were submitting to some place. So the referee said, see, AI conferences, right? Okay, fine, great. You did this images, fine. But we have moved on from images, right? Of 0 1s, right? Can do faces, can be human faces, right? So now here, then you must extend this to what is known as continuous values. Instead of 0 1 can emit continuous values. Of course, more trouble in the, but it finally worked. These are all synthetic images, by the way. There's no human being. It's not images of a person. So you can do this. Right? Okay. Now what? This is all I wanted to say, right? And now, what I want to say is not to brag. It is about. I would definitely request all of you to take a look at this paper, right? And right. So thanks for listening. But before that, some closing thoughts. My goal was to cover some foundational areas in quantum machine learning. That this is where you have to foundationally we all have to apply our mind to see if the area is successful or not. It's not about how to apply it, right? And it's very clear to me that at least 2-3 things. One is stochastic optimization. Another is density. How do you do statistics or operators? This you don't know. More understanding of quantum physics, for example, Q rapid access, is it possible or not? If it's possible, many things are possible. HHL, what are the ramifications of this, right? Those things obviously would go a very long way. In short, machine learning with operators would, if quantum ML stands, this would be a big thing, I'll tell you. Those of you looking at these topics, please do this. Because Chandrasekhar says quantum will remain, no? So quantum remains, this has to be a thing, right? Anyway, so this thing has been done with students, Professor Patel and all the students. Now, many of the results which you saw were done with them. Adit, Abhay, and Shantan helped me with some of my slides. Adit is there. So, if you have any questions on density matrices, all blame goes to him. And he's the one who developed it from scratch, and hopefully should do more about these things. Please give him good feedback. I'm here just to present it, just to say whatever. Maybe I made some mistakes also. Who knows in his work? Okay. So thanks for listening. Good. Sorry, I volunteered you for some sessions now. So thank you again for listening.
I think it was sure that he could have, he had enough material to go till tomorrow morning also, not 8 p.m. So it was a very interesting talk covering the whole overview. And I mean, it was also technically in detail to clearly say where we stand, because this is quantum machine learning or quantum machine learning AL has been mixed up to an extent that everybody are talking about it, but where we really stand, what are the questions, and as students and as researchers for us, this was a very important talk. So we have any questions from audience? Yeah.
Sir, like we mentioned about parameterized quantum circuits and how they are very relevant to the modeling of data, and like also some shortcomings exist dependent on the Hilbert's size of the Hilbert space as we increase the number of spins. Sir, in this regard, does the dynamical feature of the circuit that we are having have any effect on the its usage for developing ML models? Like dynamical, by dynamical aspects, I mean like when one of the most common ways in which quantum computers are used is for quantum simulations. We take Ising type models and we try to model their dynamics using this circuit. So we have that information on one hand. What I would like to know is that given a parameterized circuit, is it so that its efficacy is maximum when we are in some dynamical regime or not? Like, is it correlated in some way or like independent mostly?
No, frankly, okay, short answer, no, I don't know. Not that, no, I don't know. Now, but I'll take this opportunity to say something else. Now, if you look at the XHL algorithm, see, this is, I don't know what PQC, how they are in PQC, but if I'll say Hamiltonian simulation is the thing to go, and you build circuits on that, right? Now, it is very crucial that how many time steps I run, right? Now, if you look at the quantum PCA paper, right, and even the follow-up work in Excel, it's one of the things that they also give a name for it. Like they call it the Fourier, exponentiation. So where it is critically dependent on a factor called T0, the time you run the Hamiltonian simulation. Right now, whether those how important is those simulations in getting to the circuit, that information I don't have. But if somebody builds circuits on that, yes, then that would be one of the key dynamics would play a role. And today we have exactly the number that how close do I get? That the log D UT saw, log D has an epsilon built in. That will depend on the T0 time. Right?
Question is related to computer vision. So, like in quantum circuits, like there's lots of noise when we represent the images from classical to the quantum state and do the computation and coming back to the measurements. So, how this noise at a quantum state can be handled for this computer vision problems? Like this can be a new area in computer vision. like in generative AI, right? We have lots of hallucination if we talk about the computer vision. So, like if we do like such kind of computation in quantum state, so there will be more hallucination in generative AI. So that can be a new area like to explore.
But my understanding is false, right? So currently, as I said, the simple MNIST is data set, right? There are 784 and the things are like that. What will it do? Right?
Normal.
Hallucination, yeah. So I'm saying, but first remark is at this point I don't see this quantum, this paradigm strong enough to take on the state of the art in computer vision theory. We are first challenge to begin with, right? This will come after that. On the same token, I think there's also one more way to look at it, right? Maybe that's where collective wisdom kicks in. Today I can generate figures. Though we did it was just to demonstrate the density matrix kind of thing, right? But probably we should attack new age problems where we should not be generating the same thing, which already we have. So we have to revisit. So what computation problems we can target using the new the concept of quantum computing paradigm is not clear to me. You know, so you say, should I do it? If you can, of course you should do it. But the main thing is probably we should also look for good problems where this new machine is targeted to. No point doing the same thing. You know.
Any other questions?
No, that is the paper with quantum field theory, they say that if they able to do quantum simulation, then it is lower. And then I don't know, I do not think what that. Trying to use for quantum simulation for high dimensional quantum field. Because if you want to do it, you have to look very large. You can use the number of so we have to understand and I try to make it so right so to make the original point, see this paper which is quantity paper, right, where they talk with tomography also, we must do article. So they write on a science called complex sensing. Okay, now we have to understand that a bit. The complex sensing is when different measurements can get back the original. But now, because there are some new conditions behind it. So, maybe when we talk about use of tomography, we have to understand that what conditions the density matrix. I don't have an idea on that, but those are things that we should understand this, and then we will come back to it.
Sir, one of the slides you mentioned on current limitation that no algorithm to deal with density operator latent variable models. Density operator latent variable models.
Right.
Currently, no algorithm to deal with this.
Right.
But how have you dealt with this shortcoming in your DOEM paper?
Yeah, okay. So what I meant was, I said, right, algorithm of course will exist. So we taken the qualified question, right? Can this run on index? Okay. That's the reason. So all of them, because of the way they attack this problem, is they expect a 10, 12 speed. Now, if I have to map index kind of thing, right? Lot more things has to be done. And one of the important that is, you have to come up with an EM like
Expectation.
No.
How have you used this expectation maximization algorithm? That's what I want to know.
That's
Oh.
Yeah. So yeah. So maybe we can talk more. But the science has to. Sorry, the paper has some more.
I tried to go through this before I came here. I got to know latent variable models, how joint distributions you are using one of the unobserved. Yeah.
But I think we love to have feedback on this. So the main challenge in that field is trying to get new government problems. Machine learning people, we actually come with people to distribute. We do not know how to do it. So something need operator. For example, a simple thing. You take a program, daily, conditional problem. There are people who are going to fight. You fight about here. Now here, this standard technique of conditionality. Operator, what are the next to get you concerned? So these challenges show up in our EM. So there's a long sort of it. So what is exactly the difference? This is one of the first things. Then there are other things.
So I have a last question because you covered one of the aspects of using quantum principles to improve machine learning algorithms. Yeah, log. And then there's another aspect of circuit parameterization or even RP signal group. They are also trying to look at using machine learning techniques for experimental advantages or to help understand something. And there's also another where you have a quantum system. And then also algorithms, machine learning algorithms are also quantum mechanical principles. So are there any work in that third aspects of research, or is it still like? No, I have a system also quantum mechanical. And it's a function, quantum mechanical functions, and then something like that. So I need an algorithm, which is also a quantum algorithm, a quantum machine learning algorithm. So which means that it runs on the principles of quantum mechanics. So first class of problems were classical problems we had. You improved using principles of quantum mechanics to improve it. And the other one is a quantum mechanical system where we do tomography using classical machine learning techniques. So it's both
problems machine learning can help in understanding quantum systems.
Yeah, quantum machine learning algorithms can help quantum system better. Both should be quantum mechanical here. Like algorithm is quantum mechanical, system is quantum mechanical.
So, with some colleagues at Chalmers University, there is a paper published last year, where there is something. So this is okay. First of all, I think slow has not come out, but these are QML, not ML, not quantum, but QML.
Human.
That has not happened yet.
Yeah.
So we don't know. Now, this newspaper, I invite you to read this. So there, they were excited to understand. There is something called what is this? Right? How do I get, now suppose quantification is a collection of a distribution. That's what it is. So now what we could do is using like the guide your faces now that we know what it is. So there's something called textual net. There's a technique in public to understand properly. So we could vary, okay, that was there before, but we could vary the way to least square spread and all that. The theoretical bound to show that, the particular range line is an idea. And what makes it I'll make a mistake, I'm sure, as I said. So please friends that that's what my job is. So this is what I think we have an ingredient to analyze. And we apply this.
Yeah, I think that's probably
You can say something, but I'm
those are the hard problems in quantum mechanical systems. That when you have open system and invariance has to be solved, and you need to use technique.
No, so it's actually important. These are very important. We need a good playground to develop this.